In the past years, drones have been increasingly used in the healthcare field. Our rescue delivery system aims to deliver medical supplies to those in need using unmanned aerial vehicles. RED is specifically designed for those emergency situations where a fast and precise response is required. The system is comprised of a fixed-wing mothership and a multi-rotor which carries the payload.
Innovative aspect of our project is that we are integrating speed, range, and precision. The fixed-wing mothership gives range and speed to the system, whereas the multi-rotor gives the precision to the system. Our project is divided into several subsystems comprising of structures, aerodynamics and stability, propulsion, avionics, software, and two specialized subsystems, which is the docking system, which is the interface between the mothership and the multi-rotor, and the deployment system, which is the package releasing system.
Our concept of operations is divided into 5 main stages. First, the mothership and the multi-rotor in the dock configuration are loaded with the payload and the coordinates of the delivery location. Next, they fly to this location. Upon arrival, the multi-rotor detaches and conducts precise delivery of the payload. Once the delivery is complete, the rendezvous is initiated. After they rendezvous together, the docking procedure occurs, and once docked, both vehicles return back to home base in a dock configuration.
So the mechanical engineers on the team are responsible for the design of the package deployment system and the drone docking system. The drone docking system consists of a creased foam plate which guides a probe which is on top of the drone to a rectangular rail at the end of the plate. At the end of the rail is a pressure switch, which when depressed actuates the door, locking the probe in place and hence the drone. On the other hand, we have the deployment system, which consists of 2 claws where the package is gripped on either side. When the claws swivel open, the package is dropped. The claws swivel around 2 aluminum rods, which are actuated by 2 servo motors through a set of gears.
So the structure subsystem is necessary to maintain the structural integrity of the system. The mothership has a lot of components that are already pre-made, but further modifications need to be made to the system to ensure that we can fit the docking system and deployment system. Along with that, this subsystem also needs to design and develop a landing gear system so that we can maintain our clearance for the docking system and deployment system.
So all the major structural modifications on our system gave us a lot of aerodynamic challenges. So to deal with the massive aerodynamic drag, we used a lot of computer softwares like MATLAB and ANSYS Fluent to compute the flight performance and stability characteristics to ensure that our system was laterally, directionally, and longitudinally stable.
The software subsystem is responsible for ensuring that each stage of the mission can be executed autonomously. Each aircraft has a Raspberry Pi that is responsible for determining the mission phase by taking an input from GPS modules, cameras, external sensors, and each stage has specific responsibilities for each aircraft. Those responsibilities are completed when the Raspberry Pi sends custom flight commands to their attached Pixhawk flight controllers. The most challenging mission stage is autonomous docking. This is because GPS alone is not precise enough to allow for a safe and autonomous docking, so a 2-phase process needs to be implemented. In the first phase, we use the GPS location to get the multi-rotor as close in proximity to the mothership as possible. In the second phase, a camera attached to the Raspberry Pi is used to detect an Iruka marker that's located on the docking mechanism of the mothership. By detecting this marker, the Raspberry Pi can determine the absolute position of the multi-rotor and make correctional flight path commands to get the multi-rotor into its ideal docking position, at which point the multi-rotor executes its final series of docking commands. The aircrafts have a constant exchange of GPS data by utilizing internet-capable devices to publish and extract the GPS data through a real-time database.
The control subsystem is responsible for the precise flight commands required for docking. The controller we got for this project already comes with a lot of basic flight commands for stability and movement. What we did is we built on top of this existing infrastructure. The controller will take visual data and convert it into positional data. Meanwhile, the docking script will provide the multirotor with the position that it needs to be in. Finally, the controller will take the difference of these two positions and generate corrective commands that the multirotor will take in order to dock.